In this lecture, we will discuss several important groups of matrices, and as an application, we will consider Einstein's special relativity theory. The most general matrix group is the group GLNF. So these are invertible n by n matrices with entries in a field F. The notion of a group is the axiomatization of the concept of symmetry, and typically groups appear as symmetries of a certain structure. In particular, this group, which is called the general linear group, is the group of symmetries of a vector space Fn. Symmetry transformations that preserve the structure of a vector space may be interpreted as n by n invertible matrices. This group has an important subgroup, which is called SLNF, or Special Linear Group. So this consists of matrices A in GLNF with the property that determinant of A is equal to 1. And since the determinant of a product is equal to the product of determinants, this set is closed under multiplication of matrices, and it's also closed under inversion of matrices. So this means that this set forms a subgroup inside GLNF. In terms of symmetry, elements of the special linear groups can be described as linear transformations that preserve volume and orientation. In today's lecture, we will be mostly interested in cases when the field F is either real numbers or complex numbers. The next group that we will discuss today will be the set of On of R. So these are orthogonal linear operators. And in terms of symmetry, so these are symmetries of Rn as a Euclidean vector space. So that is, so this must preserve the vector space structure plus preserve the scalar product. What does it mean that a transformation T from Rn to Rn preserves a vector space structure? So this means that for all u and v in Rn, we must have T of u plus v is equal to T of u plus T of v, right? So because addition of vectors is one of the operations of a vector space. What's the second operation in a vector space? It's multiplication by scalars. So this means that for all scalars in R, we must have T of C times U is equal to C times T of U. So this means that this transformation preserves multiplication by scalars. And finally, what does it mean that this transformation preserves the dot product? This means that the dot product of T of U and T of V is equal to the dot product of u and v. Let us state a proposition that describes orthogonal linear transformations. Proposition. Let A belongs to GLNR. The following conditions are equivalent. One, A preserves the dot product. For all u and v in Rn, we must have that the dot product of AU with AV is equal to u dot v. 2. A preserves lengths of vectors and angles between vectors. 3. A preserves lengths of vectors. So this means that for all u in Rn, the length of AU is equal to the length of u. 4. A preserves the unit sphere. So this means that for all u in Rn, if length of u is equal to 1, then the length of AU is also equal to 1. 5. A transforms any orthonormal basis into an orthonormal basis. Six. A transforms the standard basis into an orthonormal basis. And 7, A transpose times A is equal to identity. Well, and let's throw in 8 for good measure. So 8 is that A inverse is equal to A transpose. We're going to show that all of these conditions are equivalent to each other, and that a matrix that satisfies this condition is called the orthogonal matrix. Let us show that 1 implies 2. We know that the length of a vector can be written as a square root of the dot product of v with itself. And then if we take the length of AV, so this is the square root of the dot product of AV with AV, but because A preserves the dot product, so this is the same as the dot product of V with V, and this is the length of V. And so here we prove that the length of AV is equal to the length of V, so A preserves lengths of vectors. The same argument works for angles. So because if we have two vectors, u and v, then the angle between these vectors is cos inverse of the dot product of u with v over the square root of u dot u and square root of v dot v. But because A preserves the dot product, so this is the same as cos inverse of AU dot product with AV over the square root of AU with AU and AV with AV. But this is the angle between vectors AU and AV. Now, the fact that 2 implies 3 is trivial, because if A preserves both lengths and angles, it certainly preserves the lengths of vectors. Likewise, it's immediate that 3 implies 4. Let us show that 4 implies 3. So we take an arbitrary vector v in Rn and let the length of this vector be c. Then the vector u, which is 1 over c times v, is a unit vector. So length of u is equal to 1. Then what is the length of AV? So v is c times u. So we have a applied to c times u. And a is a linear transformation. So this is c times a of u. And c is a positive constant. So the length of c times a vector is c times the length of this vector. But by 4, so we know that a preserves the unit sphere. So the length of AU is equal to 1. So this is c, and this is the length of vector v. And here we see that the length of a vector v is preserved. Let us now show that 3 implies 1. So for this, we will consider the quadratic form, q of v, which is the dot product of v with v. And the condition that A preserves lengths of vectors can be written that for all v in Rn, q of AV is equal to q of v. But we have seen that the scalar product may be expressed in terms of the corresponding quadratic form. We know that the dot product u dot v can be written as 1/2 q of u plus v minus q of u minus q of v. Then, if we take the dot product of AU with AV, so this is 1/2 q of AU plus AV, or which is the same as A of u plus v, minus q of AU minus q of AV. But because A preserves the quadratic form, so q of AV is the same as q of v, then we get that this expression is equal to the one on the previous line, which is the dot product of u dot v. And so this shows that A preserves the dot product. At this point, we prove that conditions 1, 2, 3, and 4 are all equivalent to each other, because we proved that 1 implies 2, 2 implies 3, 3 is equivalent to 4, and also 3 implies 1. Now let us show that 1 implies 5. Let u1 through un be an orthonormal basis. Over n. Then the dot products ui with uj is equal to 1 if I is equal to j, and 0 if I is not equal to j. But transformation A preserves the dot product. So this means that AUI with AUJ has the same value. So it's 1 if I is equal to j, and 0 if I is different from j. And then this implies that the set AU1, AU2, AUN is an orthonormal basis. Well, it's an orthonormal set, and we know that every orthonormal set is linearly independent and thus forms a basis. Now, the fact that 5 implies 6 is trivial, and let us show that 6 implies 7. So let's assume that 6 holds. Then we know that the columns of A form an orthonormal basis, because this is how we construct the matrix of a linear transformation. We put images of standard basis vectors as columns. But now let us look at the product, A transpose times A. When we take this product, we take rows of A transpose and compute the dot products with columns of A. But the rows of A transpose are columns of A. So here we're computing dot products between different columns of A. And because the columns of A form an orthonormal basis, when we take the dot product of two distinct columns, we'll get 0. And if we take a dot product of a column with itself, we get 1. And this shows that the product of A transpose times A will have 1s along the diagonal and 0s elsewhere. So this is the identity matrix. And of course, it's immediate that 7 is equivalent to 8. Finally, let us show that 7 implies 1. So if we assume that A transpose times A is equal to identity matrix, this implies that A preserves the dot product. Now, what is the dot product of AU with AV? So in terms of matrix product, so this is AU transpose times, in the sense of now a matrix product, with AV. But the transpose of AU is U transpose times A transpose. So this is U transpose times A transpose times A times V. But by 7, A transpose times A is identity. So this is equal to U transpose times V, or the dot product of U and V. And this shows that A preserves the dot product. Now, this proved that 1 is equivalent to 5, 6, 7, and 8. And hence, all 8 conditions are equivalent to each other. Let us point out that the condition that A preserves the unit sphere is a geometric condition. It is nice to think of orthogonal transformations as symmetry transformations of a geometric object. Since we interpreted orthogonal transformations as symmetry transformations, we conclude that ON of R is a subgroup in GLN R. So this means that this set is closed under multiplication and inversion. And indeed, so if we have two linear transformations that each preserve the lengths of vectors, then their composition will also preserve lengths of vectors. Let us think, what can we say about determinants of orthogonal transformations? Orthogonal transformations are characterized by the condition that A transpose times A is equal to identity. Let us apply determinant to both sides. So we get determinant of A transpose A is equal to determinant of identity. And this implies, because determinant of A is equal to determinant of A transpose, and determinant of a product is the product of determinants, so we conclude that determinant of A squared is equal to 1, and thus we get a lemma that says that if A belongs to orthogonal group, then determinant of A is either +1 or -1. This allows us to consider SONR. So this is intersection of ONR with SLNR. And this is called the special orthogonal group. What can we say about eigenvalues of orthogonal transformations? Well, suppose AV is equal to lambda times V, where lambda is a real number. Then we know that orthogonal transformations preserve lengths. So this means that the length of AV is equal to the length of V. But V is an eigenvector, so this is the length of lambda times V, which is absolute value of lambda times the length of V. And this gives us a lemma that if A is an orthogonal transformation and V is an eigenvector, AV is equal to lambda times V, where lambda is real and V is non-zero, then this implies that lambda is plus or minus 1. Now let us look at orthogonal groups in low dimensions. Let us look at the case when n is equal to 2, and suppose A is a matrix in the orthogonal group O2R. According to our proposition, A transforms the standard basis E1, E2 into an orthonormal basis. Now let us look at the geometry of this. So here we have a unit circle and two standard basis vectors on a plane. The image of E1 must be a unit vector, so it must belong to this circle. So this means that we can write AE1 as a vector cos alpha times sine alpha, because every vector on a unit circle can be written in this way. Then what can we say about the image of E2? The image of E2 must be perpendicular to AE1. So this means that there are only two places where the image of A2 could be. So it could be either here or here. Let us consider these two cases. So case 1. AE2 is in this location. And so here the coordinates of this vector will be minus sine alpha times cos alpha. Well, it's clear that we have to choose a unit vector so that these two vectors have a zero dot product. In this case, the matrix of A is obtained by placing these as first and second column. So then we get cos alpha sine alpha minus sine alpha cos alpha. And we see that this is a rotation matrix, R alpha. So we get the rotation matrix. In the second case, we choose AE2 to be this vector. So this is the opposite of this one. So it will be sine alpha minus cos alpha. In this case, the matrix is, the first column is cos alpha sine alpha, and the second column is sine alpha minus cos alpha. This matrix has the property that if we square it, then we will get the identity. And geometrically, this is a reflection with respect to a line. Specifically, if we say that AE2 is here, then this will be the axis of reflection. So we see that both E1 and E2 is reflected with respect to this line. And we conclude that there are two types of transformations in the group O2. So these are rotations by an arbitrary angle, and these are reflections with respect to arbitrary lines that pass through the origin. This classification may be described in terms of determinant. So if A belongs to O2 and determinant of A is equal to 1, so this implies that A is a rotation R alpha for some alpha. And if determinant of A is equal to -1, then this means that A is a reflection. So we know indeed that every rotation has determinant +1, well, just by calculating the determinant of this matrix, and every reflection has determinant -1 because it has two eigenvectors. So one with eigenvalue lambda equals 1, so on the axis of reflection, and the perpendicular vector will be an eigenvector with lambda equals -1. And the determinant of a matrix is the product of its eigenvalues. The group SO2 is then interpreted as the group of rotations of a circle. And in particular, this group is abelian, since all rotations commute. Next, let us look at the three-dimensional situation. And let A belongs to the group O3. So that is an orthogonal transformation of a three-dimensional space. An important difference between two-dimensional and three-dimensional orthogonal transformations is that three-dimensional orthogonal transformation have eigenvectors. So any such transformation has a real eigenvector. The reason for this is that the characteristic polynomial of A will be a cubic polynomial, and any cubic polynomial with real coefficients has a root in real numbers. So simply because at -infinity it will have one sign, and at +infinity it will have an opposite sign, so in between there will be a root. And then we proved that the real eigenvalues of orthogonal transformations could be either +1 or -1. So we must have a vector such that AV is equal to V, or AV is equal to -V. We point out that this is not the case for two-dimensional orthogonal transformation. If we take a rotation in any angle different from 0 or 180 degrees, then this rotation will have no real eigenvectors, because any vector on the plane will be rotated by a certain angle. This situation can be also interpreted in the following way. We can say that A has a one-dimensional invariant subspace. Let us prove a general result about invariant subspaces of orthogonal transformations. Let A be an orthogonal transformation, and let subspace U in Rn be invariant under A. Then the subspace U perp is also invariant under A. We recall that U perp is defined as a set of vectors W in Rn such that for all U in the subspace U, the dot product of U with W is equal to 0. So it's the set of all vectors that are perpendicular to all vectors in the subspace U. Since U is invariant under A, we can view A as an operator on the subspace U. And we point out that this transformation is injective because A has no kernel in Rn. Well, after all, every orthogonal transformation is invertible. And because we have an injective operator, automatically it follows that this operator is surjective on U. Let W belong to U perp. To prove that U perp is invariant under A, so we need to show that A applied to W is also in U perp. This means that for all U in U, the dot product of U with AW must be 0. But A is surjective on U, so this means that for every U in U, there exists V in U, such that U is equal to A applied to V. But then the dot product of U with AW is equal to the dot product of AV with AW. And the A is an orthogonal transformation. It preserves the dot product. So this means that this is equal to the dot product of V with W. But W belongs to U perp, and V belongs to U. So this means that this dot product is equal to 0, and we proved that indeed AW also belongs to U perp. Now let us return to the situation of a three-dimensional orthogonal transformation. So we saw that such a transformation has an eigenvector, and so this eigenvector will give us an invariant line, and by proposition, the two-dimensional plane, which is perpendicular to this line, will also be invariant under this transformation. So this means that this transformation A will act on this two-dimensional subspace. Since A preserves the dot product on R3, it also preserves the dot product on this two-dimensional subspace. And then this means that A is an orthogonal transformation of this two-dimensional subspace V perp. But now we understand the geometry of orthogonal transformations of two-dimensional spaces. So we know that A is either a rotation of V perp, or A is a reflection with respect to a line in V perp. But in the latter case, so we can see that A is diagonalizable with eigenvalues plus minus 1. Indeed, a reflection with respect to a line has two eigenvectors, one eigenvector with eigenvalue plus 1 and one eigenvector with eigenvalue minus 1. But there is a third eigenvector which is perpendicular to this line, so this is the vector V. And then in this case we conclude that A has a basis of eigenvectors. So let us formulate the geometry of transformation A in the first case. So here we have that if AV is equal to V and A is a rotation of the plane V perp, then as a three-dimensional transformation, A is a rotation of R3 around the axis spanned by V. In the second case, so if AV is equal to minus V, then A is a composition of a rotation of R3 around axis given by vector V with reflection with respect to the plane Vperp. So what we will have is we will have a plane in a three-dimensional space, and the transformation is a rotation in this plane together with mirror symmetry with respect to this plane. Finally, let us look at the diagonalizable case. In this case, there will be a basis where A has one of the following four matrices. So the first case is the identity transformation. So this can be interpreted as a rotation in angle alpha, which is 0. In the second case, we have a single eigenvalue minus 1. So this can be interpreted as a reflection in a plane spanned by the other two basis vectors. In the third case, we have one eigenvalue plus 1 and two eigenvalues minus 1. This can be interpreted as a rotation in angle alpha, which is 180 degrees. Here we consider a plane spanned by the second and the third basis vectors, and the rotation of this plane in 180 degrees will turn each of these vectors in its opposite. And the last case is when we have minus identity transformation. So this can be interpreted as a reflection together with a rotation in 180 degrees. We conclude that the diagonalizable case also can be incorporated in these two cases, when we have a rotation around some axis or a composition of a rotation with a reflection. And we see that the first case corresponds to the case when determinant of A is equal to plus 1, while the second case corresponds to the case when determinant of A is equal to minus 1. As a consequence of this discussion, we get a geometric interpretation of the group SO3. So this group is the group of rotations of a sphere. So each such a transformation will be characterized by the axis of rotation and the angle of rotation. Next, let us look at the unitary transformations. So we take the set of unitary transformations. UM. These are symmetries of the Hermitian vector space Cn. So these are linear operators A from Cn to Cn, preserving the Hermitian scalar product. So this means that for all u and v in Cn, we have that the Hermitian scalar product of Au with Av is equal to the Hermitian scalar product of u with v. And because the right-hand side can be written as U bar transpose times V, and the left-hand side can be written as U bar transpose times A bar transpose times A times V, then we see that A is unitary if and only if A bar transpose times A is equal to identity. And let me give you an exercise. Formulate and prove other conditions that are equivalent to A being unitary, just as we have done for the case of orthogonal transformations. Since the set of unitary transformations is defined as a set of symmetries of a certain structure, it automatically follows that this set forms a group, which means that the product of two unitary transformations is unitary, and the inverse of a unitary transformation is also unitary. What can we say about the determinant of a unitary transformation? So we have the following lemma, that determinant of a unitary transformation A has complex norm 1. Let us take the identity that A bar transpose times A is equal to identity matrix and take the determinant of both sides. Then on the left we get the product of determinant of A bar, and the transpose does not change the determinant with determinant of A, and on the right we have 1. But the determinant of a conjugate of a matrix A is the conjugate of determinant of A, and this tells us that determinant of A conjugate times determinant of A is equal to 1, and that exactly says that the complex norm of determinant of A is equal to 1. So the determinant of a unitary transformation can be a complex number, but this complex number must have complex norm 1. We define the special unitary group denoted SUN as the intersection of UN with SLN C. These are unitary transformations with determinant 1, and they will form a subgroup inside UN. Let us look at the group U1. Here, the condition that A bar transpose times A is equal to identity. So in this case, A is a 1-by-1 matrix, so it becomes A bar times A is equal to identity. So this means that this 1-by-1 matrix will have a complex number of norm 1. Such numbers lie on a unit circle and can be parameterized as e to the I alpha, where alpha is a real angle. And then we see that this group is isomorphic to the group SO2R, because multiplication by e to the I alpha may be interpreted as a rotation of a circle by angle alpha. Let us look at the eigenvalues of unitary transformations. So if we have AV is equal to lambda V, since A is unitary, it preserves the Hermitian scalar product. So this means that scalar product VV is equal to the scalar product of AV with itself. But V is an eigenvector, so this is equal to lambda V with lambda V. This product is sesquilinear, so when we pull out lambda from the second factor, it just comes out, and when we pull it out from the first factor, it comes out with a complex conjugate. So this is equal to lambda times lambda bar times VV, or this is a complex norm of lambda squared times VV. And we state this as a lemma, that if A is a unitary transformation and AV is equal to lambda V, with V being non-zero vector, then the complex norm of lambda must be equal to 1. Let us state a proposition about invariant subspaces for unitary transformations. Let A be unitary and let U be a subspace in Cn, which is invariant under A. Then the subspace U perp is also invariant under A. The proof of this proposition is exactly the same as in the case of orthogonal transformations, and I leave it as an exercise. Now let us prove the spectral theorem for unitary operators. Let A be a unitary operator. Then there exists an orthonormal basis V1 through Vn of Cn consisting of eigenvectors of A. So this means that A applied to Vk is equal to e to the I alpha k times Vk, where k goes from 1 to n. Proof goes by induction in n. So the basis of induction when n is equal to 1, so we already saw that in this case the transformation is multiplication by a complex number of norm 1. So this means that this statement of the theorem holds. And the induction step we assume that theorem holds for Hermitian spaces of dimension n-1. Since A is an operator on a complex space, A has an eigenvector. We can set V1 to be this vector divided by its length. This will give us an eigenvector of length 1. And we know that eigenvalues of unitary operators lie on a unit circle. Next, we consider a subspace W, which is V perp. By proposition that we proved, this subspace is going to be invariant under A. We know that W is a Hermitian space of dimension n-1, and A will preserve the Hermitian scalar product. So this means that A becomes a unitary operator on W. And then, by induction assumption, there exists an orthonormal basis of W, we can call it V2 through Vn, that consists of eigenvectors of operator A. So this means that A Vk is e to the I alpha k Vk. And then adding to this basis the vector V1, which is orthogonal to all of these, will give us an orthonormal basis of Cn that we require. And this completes the proof of the spectral theorem. We saw that in general, orthogonal transformations are not diagonalizable. But what can we say about the structure of these transformations? Theorem. Let A be an orthogonal transformation. Then there exists a decomposition of Rn into a direct sum of subspaces U1 plus U2 plus UK, such that first, each subspace is invariant under A. Secondly, all subspaces Uj are orthogonal to each other. Thirdly, dimension of each subspace is equal to 1 or 2. So if dimension of Uj is equal to 1, then A acts on Uj with eigenvalue +1 or -1. And finally, if dimension of Uj is equal to 2, then A acts on Uj as a rotation in angle alpha j. This theorem generalizes the structure of orthogonal transformations that we derived for the case of R3. So here we decompose Rn in a direct sum of mutually orthogonal subspaces, where each subspace is either a line or a plane, and on each plane this transformation will act as a rotation in its own angle, and on each line it either acts as identity or as a reflection. The proof of this theorem will go by induction on n. And the basis of induction, n equals 1, is the trivial case. Let us do the step of induction. We assume that the claim of the theorem holds for orthogonal transformations on n-1 dimensional Euclidean spaces. Now let us consider two cases. So case 1. A has an eigenvector in Rn. Necessarily, so this eigenvector will have eigenvalue either +1 or -1. Then we set U1 to be the span of this vector, right? So this will be a one-dimensional invariant subspace. And we also consider W to be the orthogonal complement of this vector. And W will be Euclidean subspace of dimension n-1. Then by proposition that we proved, A becomes an orthogonal transformation on n-1 dimensional Euclidean subspace. And then applying the induction assumption to W, so we get the claim of our theorem. Now, the more interesting case is case 2, when A has no real eigenvectors. In this case, we will complexify the space, and so we consider the complexification Cn, which is Rn plus I Rn. And then any real orthogonal matrix is unitary. Thus, A may be interpreted as a unitary transformation on Cn. And then, as a unitary transformation, it must have an eigenvector. So we must have a non-zero vector in Cn such that A applied to V is e to the I alpha times V, and V is non-zero. Let us take this vector and consider its real part and imaginary part. So we're going to write V as U plus IW, where U and W are now in Rn. Then let us write down this equality. So this equality says that A multiplied by U plus IW is equal to e to the I alpha, to which we apply Euler's formula and write cos alpha plus I sine alpha, times V, which is U plus IW. Now, A is a real matrix. So when we apply a real matrix to a real vector, the result is real. So extracting a real part and imaginary part of this equality, we will get that AU is equal to cos alpha times U minus sine alpha times W. And if we take the imaginary part, then we get that AW is equal to sine alpha times U plus cos alpha times W. And this tells us that the subspace U, which is the span of U and W, is invariant under A. And because we're considering the case when A has no real eigenvectors, so this means that A has no one-dimensional invariant subspaces, it follows that dimension of U is equal to 2. Now, A is an orthogonal transformation of a plane. And we know the structure of orthogonal transformations on a plane, so it's either rotation or reflection. But reflections will have eigenvectors, and here A does not have eigenvectors. So this means that A is a rotation of this two-dimensional plane U. And then we set W to be an orthogonal complement of U in Rn, and W is A invariant. And applying the induction assumption to the subspace W, we obtain the claim of our theorem. To introduce the next matrix group, we consider the space Rn with a non-degenerate symmetric bilinear form given by some symmetric matrix J. So this means that the value of the bilinear form on U and V is given as U transpose times matrix J times vector V. We define the group O of J as linear operators on Rn, preserving this bilinear form. So this means that for all U and V in Rn, we must have that AU with AV is equal to the value of the bilinear form on UV. Now, the right-hand side can be written as U transpose times J times V, and the left-hand side can be written as U transpose times A transpose times J times A times V. So we see that an equivalent description of this group is the set of matrices A in GL and R such that A transpose times J times A is equal to J. We know that non-degenerate symmetric bilinear forms on Rn are determined by their signatures. So if the signature of this bilinear form is PQ, this means that in a certain basis, matrix J can be written as P plus ones and Q minus ones. So we have P of these and Q of those. Then another notation for this group will be OPQ, where N is equal to P plus Q. And by taking a subgroup of transformations with determinant 1, we also get a subgroup SOPQ as a subgroup here. Next, let us going to see which role matrix groups play in special relativity theory. We will begin with Galileo's relativity in classical mechanics, which postulates that all laws of physics are the same in orthonormal inertial coordinate systems. Then it states that any coordinate system, well, orthonormal coordinate system, that moves with a constant velocity relative to a given inertial system is also inertial. And we have the following principle of vector addition of velocities. Suppose we have two inertial coordinate systems. One and two, with system 2 moving with velocity vector v relative to system 1. Suppose an object is moving with velocity vector w relative to system 2. Then the velocity vector of this object in system 1 is given by the vector addition of the two velocities. Before Einstein's, these were considered as universal principles of physics. But now we understand that this is only an approximation of the true laws of physics at low velocities. During the 19th century, we got a much better understanding of electromagnetic phenomena, culminating with Maxwell's equations for the electromagnetic field. And in particular, it was realized that light is an electromagnetic wave. Maxwell's equations incorporate c, the speed of light, as a universal constant. So this constant appears explicitly in Maxwell's equations. Now, this may create a collision with Galileo's relativity. Well, imagine that we have a spaceship that moves at the velocity which is half of the speed of light. And suppose this spaceship shines light in the direction of its travel. Then what would be the speed of light for a stationary outside observer? By applying Galileo's relativity principles, we might conclude that the speed of this beam of light is 3/2 of the speed of light. But this would contradict the Maxwell's equations. To get around this contradiction, physicists contemplated the idea that light travels in a special medium called ether. And then a beam of light travels with the speed of light relative to ether, regardless of the speed of the object that emitted this wave. Then any material object, for example our planet, will move relative to this ambient ether. Then in 1878, Michelson and Morley decided to run an experiment to measure the velocity of the Earth relative to this ambient ether. What they did is that they assembled a device that can be used to measure the speed of light with a high precision and mounted it on a turnable platform. And then they expected to see the difference in the measurement of the speed of light if they align this platform in the direction of the motion of the Earth. compared to turning this platform 90 degrees. However, this experiment failed. That is, they detected absolutely no difference in the speed of light measured in any direction. This put physics in the state of a deep crisis, because now physicists no longer understood propagation of electromagnetic waves. This crisis was resolved in 1905, when Einstein proposed a truly remarkable special relativity theory. Einstein's idea was to put space and time together and form a single space-time, which is R4, with vectors of the form x, y, z, and t, with a symmetric bilinear form, with a matrix given by a diagonal matrix 1, 1, and then minus c squared, and zeros elsewhere, where c is the speed of light. This generalized the usual Euclidean distance, and so if we write the quadratic form of a vector v, then this will be x squared plus y squared plus z squared minus c squared t squared. And what we see is that this quadratic form is not positive definite. And then admissible coordinate transformations in space-time are those that preserve this bilinear form. So if we denote this matrix by J, then we are looking at the matrices satisfying the properties that A transpose times J times A is equal to J. Or equivalently, for all U and V in R4, we will have that the bilinear form of UV is equal to the bilinear form of AU with AV. For calculations, it is convenient to choose the units of time so that to make c equals 1. So if the unit of length is 1 meter, then the unit of time will be approximately 3.3 nanoseconds. And then the relevant group of symmetries of spacetime will be the orthogonal group O31, where 31 is the signature of this bilinear form. To understand the phenomena of special relativity, it is sufficient to take a simplified model where we take as a spacetime R2 with one spatial and one time component. Notice here that points in space-time should be interpreted as events, because these points have not only the spatial component, but also they have a specified time. So here we set the speed of light to be 1. So the matrix of the bilinear form is a 2 by 2 matrix, 1, 0, 0, minus 1. And the symmetry group is O, 1, 1. Let us describe matrices that belong to this group. This group will consist of 2 by 2 matrices A, B, C, D, such that A transpose times J times A is equal to J. Let's do the calculations. So if we take A transpose, so this is ACBD times 1, 0, 0, minus 1 to A times ABCD, when we multiply the first two factors, we're going to get A minus C, B minus D, and times ABCD. So this will become A squared minus C squared. So here we will get AB minus CD. Here we get AB minus CD. And here we get B squared minus D squared. And this must be equal to the matrix J. So we get the following equations. A squared minus C squared is equal to 1. B squared minus D squared is equal to minus 1. And AB is equal to CD. The last equation can be written as B over C is equal to D over A. Let us call this quotient as P, and then we get that B is equal to P times C, and D is equal to P times A. Then from the second equation, we get that 1 is equal to D squared minus B squared, which is equal to P squared times A squared minus C squared. And then comparing this with the first equation, we conclude that P must be equal to plus or minus 1. So we either have that D is equal to A and C is equal to B, or D is equal to minus A and C is equal to minus B. Well, in any case, C squared is equal to B squared. And so let us look at the equation. A squared minus B squared is equal to 1. And let us think, how can we solve this equation? If we had the equation A squared plus B squared is equal to 1, this would give us a unit circle. And then we know that we have a parameterization of a unit circle with cos alpha and sine alpha. Here we need to use hyperbolic trigonometric functions, where cos hyperbolic of alpha is defined as e to the alpha plus e to the minus alpha over 2, and sine hyperbolic of alpha is equal to e to the alpha minus e to the minus alpha over 2. It is straightforward to verify the most fundamental identity for the hyperbolic trigonometric identities, that cos hyperbolic squared of alpha minus sine hyperbolic squared of alpha is equal to 1. These functions are called hyperbolic because this will give us a parameterization of a hyperbola. And the solution of this equation will be A is equal to plus minus cos hyperbolic of alpha, and B is equal to plus minus sine hyperbolic of alpha. We are going to choose only positive signs in this parameterization. So we will consider matrices cos hyperbolic alpha, sine hyperbolic alpha, sine hyperbolic alpha, and cos hyperbolic alpha. This group is denoted as SO11 plus. Choosing negative signs either here or here will correspond to reversing the direction of x or reversing the direction of time. Now let us look at the change of coordinates. Where the standard coordinates xt are equal to change of basis matrix, times the coordinates relative to another basis, where matrix C is the matrix A, B, B, A, with the condition that A squared minus B squared is equal to 1. Now, this means that we can express X as A X tilde plus B T tilde, and T is B X tilde plus A T tilde. Now, let us look at the spatial origin of the second coordinate system. So this is given by the equation that X tilde is equal to 0 and T tilde is arbitrary. What happens to this in the original coordinate system? So here we're going to get that X is, so we take into account that X tilde is equal to 0, so this becomes B times T tilde. And T is equal to A times T tilde. So what we see is that this origin is moving relative to standard coordinate system. And what is the velocity of this motion? So the velocity of this motion is given by x divided by t. And this is b over a. This means that performing these coordinate changes corresponds to going from the moving coordinate frame to the stationary coordinate frame. Now let us solve here for a and b in terms of v. So from this equality, we see that b is equal to v times a, but then we have a relation that a squared minus b squared is equal to 1. So we get that a squared minus v squared times a squared is equal to 1. So this means that a squared is 1 over 1 minus v squared, and a is 1 over the square root of 1 minus v squared, whereas b, which is v times a, so this is equal to v over the square root of 1 minus v squared. From the relation that a squared minus b squared is equal to 1, we easily conclude that a squared must be greater than b squared. And then it follows that the absolute value of v, which is the absolute value of b over a, must be less than 1. And this 1 should be interpreted as the speed of light. The physics interpretation of this is that no object can move faster than light. Now let us look at some examples. So let us look at the motion of a rod. Suppose we have a rod of length L. And this rod is moving, so this means that we consider it in the tilde coordinate system. So what will be the trajectory of this rod? So we have the left end of this rod and the right end of this rod. So the left end will have x0 tilde is equal to 0, and the right end of the rod will be x1 tilde is equal to L. And here t tilde is arbitrary. So this means that this rod is stationary in the moving coordinate system. Now let us compute the trajectories of the left and the right ends of this rod in our standard coordinate system. So here we will have that x0 is, x tilde is equal to 0, so we will just get b times t tilde. And x1 is equal to a times L plus B times T tilde. For the left end, T is equal to A times T tilde. And just as we have done in this calculation, we see that the trajectory x0 of t is v times t, where v is equal to b over a. Now, for the right end of the rod, t is given by the formula. It's b times L plus a times t tilde. Now, let us solve this system of equations. So from the second equation, we get that t tilde is equal to t over a minus bl over a. If we plug this into the first equation, then we get x1 is equal to a times L plus b over a t minus b squared L over a. And since b over a is v, this is equal to vt plus a squared minus b squared over a times L. And then we get a formula for the trajectory of the right end of the rod. x1 of t is equal to vt plus, well, a squared minus b squared is equal to 1. So we get that L over a. And we point out that this relation implies that a must be greater than 1. So what is the length of the rod in standard coordinate system? Well, the left end moves along the trajectory x is equal to vt, and the right end moves along the trajectory x is equal to vt plus L over a. So this means that the length of this rod is x1 minus x0, which is equal to L over a. And a is 1 over the square root. So this becomes L times square root of 1 minus v squared. Or if we use the units where the speed of light is not equal to 1, then this formula becomes L times square root of 1 minus v squared over c squared. And the conclusion is that a moving rod shrinks. So it gets shorter. And it shrinks in the direction of the travel. As our next example, let us look at a moving alarm clock. Suppose in the moving coordinate frame, we set up an alarm clock that generates two events. So we have one event is at the origin. So x tilde is equal to 0 and t tilde is equal to 0. So when we set the alarm clock. And the second event is when x tilde is equal to 0 and t tilde is equal to capital T. So we set the alarm clock for time capital T. What will be the corresponding events in the standard coordinate system? Well, we use these formulas and we see that this event becomes x is equal to 0 and t is equal to 0. And this event becomes x is equal to b times capital T. Well, this means that this alarm clock is moving. And t is equal to a times capital T. Now, what is the time difference between these events? In the standard coordinate system? Well, obviously, t prime is equal to a times t, which is t over square root of 1 minus v squared. And since a is greater than 1, so this is strictly greater than t. So we see that more time has elapsed in the standard coordinate system compared to the moving coordinate frame, which means that in moving coordinate frame, time slows down. And this phenomenon can be verified experimentally. If we take a beam of elementary particles with a short half-life and then use accelerator to increase the velocity of the particles to velocities comparable with the speed of light, then we will see that the half-life of these particles will increase. As a third example, so let us look at addition of velocities. So suppose we have an object that is moving with velocity w in the tilde coordinate system. So this means that its trajectory is x tilde is equal to w times t tilde. What will be the trajectory of this object in the standard coordinates? So here we will get that x is equal to ax tilde plus b times t tilde. And making a substitution for x tilde, we get aw plus b times t tilde. And t is given by the expression b times x tilde plus a times t tilde, which is equal to bw plus a times t tilde. We also take into account the relation that b is equal to v times a. So then this becomes a times w plus v times t tilde, and this is a times 1 plus vw times t tilde. And then we get the velocity in standard coordinate system will be x divided by t, and it's given by the expression v plus w over 1 plus v times w. Or if we use units where the speed of light is not equal to 1, this is v plus w over 1 plus v times w over c squared. Now what we see is that this is different from Galileo's addition of velocities. But if both v and w are much lower than the speed of light, then this is approximately equal to v plus w in the case when both v and w are much lower than the speed of light. However, if w is equal to 1, so this means that we look at the original object that moves at a speed of light in the tilde coordinate system, then this w prime, which is going to be v plus 1 over 1 plus v, is also going to be 1. So this means that if an object is moving with the speed of light in one coordinate system, then it will be moving also with the speed of light in any other coordinate system. And this shows that the speed of light is a universal constant in all inertial coordinate systems. The notion of symmetry already appeared in Galileo's treatment of mechanics. According to Galileo, admissible transformations in R3 that do not change the laws of physics are orthogonal transformations. However, Einstein put the idea of symmetry in the forefront of physics. Basically, Einstein postulated the symmetry of our space-time, and all other laws follow just from this postulate. Nowadays, the development of any modern physical theory begins with postulating the symmetry group that this theory will obey. And in particular, in 1960s, there was a development of the standard model of elementary particles. So this was developed by Glashow, Weinberg, and Salam. And they postulated that the symmetry group of this theorem is SU3, the special unitary group, cross SU2 cross U1. U1 component is responsible for electromagnetism, SU2 corresponds to weak nuclear force, and SU3 corresponds to strong nuclear interactions. By postulating this symmetry group, physicists were able to predict a great number of new elementary particles. All of these particles were subsequently discovered, which was a great triumph for the idea of using symmetry and group theory in physics.